All right. Good morning, good afternoon, and good evening, everyone. Welcome to the Redpanda Community Office Hours. I'm Dunit Dhanushkar, a senior developer advocate from Redpanda, and I'm super excited to be your host today. So today we have an amazing line of speakers who will be sharing their insights and expertise on the follower fetching, a feature which will be available in Redpanda latest release. Our first speaker today is Matt Schumpert. So Matt is our head of product core at Redpanda. In fact, Matt has been a seasoned veteran in the big data and streaming data space since the early days of Apache Kafka development. So having that experience, Matt will help us understand the high-level details of follower fetching and how it will impact your business in terms of cost savings in networking. So Matt, welcome to the show.
Thank you.
All right, and then we have our very own Michal Maślanka as our second speaker. So Michal is currently a technical lead at Redpanda, and he has contributed to so many amazing features in the Redpanda code base, especially the raft algorithm implementation and this follower fetching feature. So that's why we invited Michal to walk us through the things under the inner workings of follow fetching and how it works and relevant configuration, etc. And as a bonus point, Michal has come up with a amazing demo, so we can see everything in action. So Michal, welcome to the show as well.
Hello, thank you.
All right. So what are we going to discuss today? So let's have a look at the agenda. So like I mentioned earlier, the theme of this call is follower fetching, which is a feature which will be available in Redpanda's latest release, 23.2. So just to structure this call better, I thought of breaking it down into 3 segments. So in the first segment, Matt will talk about the follower fetching in very high level, and he'll also walk us through the real world use cases where this can be applied and how this feature can help you reduce the networking bill. And then we, in the second segment, we take a deep dive into the feature implementation. And this is where Michal comes in the scene, and he'll walk us through the sequence of events that happen when we configure this follow fetching. And also he will take us through the demo as well. And the final I'll invite Matt to talk about the things to remember when you enable this feature in production. And we'll talk about the general best practices and the things we can avoid. And also finally, we can take some couple of questions from the audience as well. So that's the plan for today. Let's get started. So my first question goes to Matt. Matt, help us understand what do you mean by follower fetching? Can you give us a bit of an introduction?
Sure, thanks, Steve. I'm happy to. I think the what of follower fetching is actually pretty straightforward. The why is probably the most interesting part, which we'll get to later, but it really depends if you are already familiar with Apache Kafka, how much explanation is needed here, because Apache Kafka has a similar capability, as we'll allude to. So first, a little bit of background, though. Prior to this feature being available in Redpanda or also in Apache Kafka, there's a very important sort of constraint around how data is consumed from topics. So despite the fact that Redpanda and Kafka both replicate data multiple times usually across the network to both improve the durability of data if there are infrastructure failures and the availability of data if you're, for example, doing maintenance on certain parts of your infrastructure. There's still this constraint that the consumers of the partitions and the topics must go to a particular replica of each partition. So there's really one and only one place from where the data can be read prior to follower fetching being added. So this effectively means that, in a typical system where you have 3x replication, really there's only 1/3 of the choice available for various consumers coming in from various directions to consume their data. So the replication is really giving you, the durability and availability, but it's not necessarily making that data available, as broadly or as closely to where the read workload is happening. And so what was proposed in KIP 392 in Kafka, and also available in Redpanda already in our 23.2 beta release that came out a few weeks ago, which will be GA at the end of July, is a similar capability, which enables the consumers to fetch records from the closest replica of any partition, regardless of whether it's a leader or a follower. So again, in a typical cluster, you might have 3x replication, 1 leader, 2 followers. Now you have 3 choices where you want to consume the data. You could have 5x replication. Now you have 5 choices. But the important thing is the closest part. And Michal will get into the details of what closest means. But first, maybe let's talk about how that can save you money, right? Something that makes everybody happy, and the other business benefits of using follower fetching.
Yes, absolutely. So that's the very reason we introduced this feature there. So could you talk about potential use cases, real-world use cases where we could use this, and how it helps us save networking costs in terms of data transfers between availability zones and regions? Could you give us some insight as well?
Sure. So there's really one big highlight and sort of top benefit, which is the first bullet there, which is this really helps shape the network traffic in a cluster that's distributed, especially over a wide area, over different availability zones, or even different cloud regions, for example, or different racks in a data center, different rooms, sort of multi-AZ on-premise setup, whatever it might be, to minimizing sort of the cost and resources consumed when you're reading data. So in the cloud, it's very pointed because the cloud providers charge when data crosses availability zone boundaries, when it crosses region boundaries, right? So every single read that's not local to an AZ or to a region is actually adding up in your cloud bill, your AWS, GCP, Azure bill, and shaping the network traffic in a way that reduces the amount of data going all across the internet between zones and regions, which costs you money, obviously saves you a lot of money. And this really depends. The benefit is very significant, but it depends on the volume of consumed traffic that you have, obviously, and the ratio of consumed to produce, as well, as we'll discuss in one of the use cases. But really, cross-AZ costs can really be a killer. And there's a number of other solutions in the market for streaming that really don't have this capability. And so you're really at the mercy of whether you have a multi-AZ deployment for disaster recovery and redundancy purposes, and where your consumed traffic is, and you might have sort of hidden and unexpected costs in terms of network traffic, right? The second one is read latency for consumers. And I want to be very specific. We want to measure the latency here for consumers in terms of how quickly that consumer can connect and read some messages from a partition and then move on to the next one. I'm not talking about end-to-end latency from the producer all the way to the consumer, because as indicated before, we're reading replicated data here. So the data is sort of asynchronously, transparently getting replicated from where it's produced over to where it's consumed, which can be from one of these followers. But from the perspective of the consumer itself, it doesn't have to reach across an availability zone or across a region, which itself just has network latency associated with it, right? So you can more quickly get to a partition if you're positioned where that partition is located, right? And that can be an advantage in certain scenarios if you're measuring just sort of the time to consume. And then the last one is, depending on your workload, you can get actually more throughput, more bang for your buck out of your cluster. Because as described previously, we're replicating the data 3x, but we're not, before follower fetching, using all of that data really for traffic, right? We're using it upon maintenance and upon failures and so forth, but we're not actually serving it up to be consumed. And therefore, assuming your load is nicely distributed, using all the network bandwidth, the IO, IOPS of the hardware, the CPU, and so forth, to actually serve requests to consume from partitions. So you're effectively kind of, making better use of the hardware by spreading it around the cluster. Those are kind of the 3 business benefits of follower fetching.
That's amazing, and thanks for that comprehensive explanation, Matt. So, yeah, just to put that what Matt has mentioned into a perspective. So we came ready with a fictitious use case where you can compare and contrast how this follow fetching can help you reduce your cost. So just imagine we have this Acme Corporation. So we have this streaming data workload running on AWS, and just say we have this ingress and egress numbers, and then we can compare this without follower fetching. So the cost will be these kind of numbers. So the total monthly cost will rack up to this number of costs. And if we compare this with follow fetching enabled, we can see the cost reduction would be about 60%. So from it's a significant decrease from $103,000 to $41,000. So that's the true beauty of follower fetching. So that's just a hypothetical example, but it would be nice to see some realistic example coming from Matt again. So Matt, would you like to walk us through this example as well?
Yeah, absolutely. And all these examples really come from interactions with folks we're talking to, with users. In this case, it's already existing customer of Redpanda, as Denise mentioned, that's already deployed and using Redpanda in production, but of course not with follower fetching yet. So they've deployed a Redpanda in Amazon and AWS using EKS, so Kubernetes cluster, using 3 availability zones already. And in fact, previously they were using Kafka, and they actually using an older version of Kafka, because follower fetching was so important to them, they manually implemented a kind of follower fetching on their own side by manually moving around partitions and mapping the nodes to the racks outside of Kafka because they couldn't do it inside of Kafka. It's just an anecdote. It happened to be an older version of Kafka, but it was a lot of sort of manual work for them. And of course, they wanted this to be automated. They had a lot of different client applications, and so they were relying on custom code that some clients were implementing and other clients were not implementing. And they just want things to be simple and transparent across the board. As you'll see later, it's very easy to have follower fetching configured and have all your clients using it with a couple simple steps. But what they are able to do now is, they estimate save up to 50% of their entire cloud spend with follower fetching. So Denise showed you kind of 60% savings on the network costs for that other example. Well, in this case, as I mentioned, it really depends on the ratio of produced to consumed traffic. If you have a lot of egress traffic, in this case, they had about 4 times the egress traffic as the ingress traffic, right? And in their case, with their costs that they have with AWS, that was approaching the entire compute cost for running the cluster. So you have your EC2 instance costs, right? And then you have your cross AZ costs because it's a 3AZ cluster. And when you take into account this large consumer load, it really adds up, makes their cluster effectively double what it should cost. So, their estimates are between 30 and 50% of their overall infrastructure spend to run this streaming cluster would be saved by using follower fetching. It's not really an extreme example. Maybe it's more than usual, but it's pretty common to have, multiple times the consume traffic that you do to produce traffic as clusters get more widely used and deployed, and that data gets used by more applications. So, obviously the bigger deployment, the more AZs, the more usage and consumer traffic you have, the more you can save.
Yeah, thanks, Matt. That's amazing. So yeah, it's always good to see examples coming from these realistic scenarios. Yeah, that's all right. Now that we have some good understanding of how follower fetching works in high level and how it helps reducing your networking costs, now it's time to take a deep dive and see what's under the covers. So this is where I would like to invite Michal to talk through the implementation details. Basically, let's try to understand how it works. Michal, over to you.
Okay, thank you. Thanks, Matt and Denise, for this overview. That was really great. I will try to go a little bit more into the details of how this is all work. So as Matt already mentioned, topics in partition. So probably most of you are familiar with this Kafka data model, but I will just briefly go over that as we are using exactly the same model in Redpanda, and this will set the stage for later understanding of the whole internals. So in Kafka, topics are actually a set of partitions that share the same configuration, and they are used to logically group your data. And Redpanda leverages Raft. So each partition is really a separate Raft instance that is used to replicate this data. And on this picture, we can see a partition deployed in multiple availability zones. So you can see 3 Redpanda clusters and these small blocks with numbers, they represent a Raft log. And Redpanda with this star marked with star is a leader. So this leader is by default receiving all the writes and reads, so all the produce and fetch requests. And as we can see here, it then replicates all the data to the followers to cross AZs. This is why this so the latest message in the log is marked with this dashed line, so that it's already committed on the leader, but it's not yet committed on the followers. This is how the notation that we use here. And now, can we go to the next slide, please? Yeah, and what Matt already mentioned, the cost, right? So using this cross AZ will always incur cost if an application that is reading the data is in different AZ. And here on this diagram, we can see that users from AZB try to communicate and read from the leader, which is in AZC. And this crosses the AZ boundaries, so that will incur an extra cost. And this is by default, because both in Kafka and Redpanda, we use a leader to coordinate replication. So all the requests go by default to the leader. But with the follower fetching, what this allows us to do is to actually read from the closest replica. So you can see here that the users, so those are the Kafka clients, they communicate with a replica that is in the same AZ. So obviously they have to, as Matt already mentioned, they have to tolerate a little bit more of the end-to-end latency. The end-to-end latency will be higher because they have to wait for this committed message, for the message to be committed on the follower for this high watermark, because this is how it's called in Kafka lingo. This is the offset of a message that is readable by consumer. It has to propagate throughout the cluster. So there will be this latency of 1 round trip. But this allows us to reduce the latency of connection and the latency of requests, and also reduce the cost. And now let's take a look at how this is worked under the hood. This is a sequence diagram presenting a simple flow of consumer trying to consume messages from Redpanda or Kafka broker. This is based on the Kafka protocol. And I, on purpose, skipped here group coordination messages, because that would be like very complicated with consumer group coordination included. But the way how it works, when the consumer wants to consume some messages, when the client is starting, it requests metadata from any broker in the cluster. And this metadata, besides the others, includes an information about partition leaders. So they say that partition 1 has leader on broker 1, partition 2 may have leader on the other broker, and so on. And this is this first step. This is used to discover, for cluster discovery and for this leader discovery. And then consumers, they are communicating directly with particular leaders, with particular brokers, requesting them to read data. And this is this next step where they send fetch request directly to the leader. And then by default, the reader responds with records data. And this, the last message is really, that's where the data are transferred from the broker to the leader. And this is what incurs this large cost, as this is where the data lives. So this is the large message. And with follower fetching, there is a slight difference in the protocol, because right now, the first step is really identical. So customer is still communicating with any Redpanda to discover leaders. And then it exchange with the leader the first message, the first fetch request, but it has this rack ID set. So you can see here that the fetch request contains this rack ID, and this is telling Redpanda broker that this consumer lives in this particular rack. And now leader knows that this consumer wants to reach from the closest replica, not any of replicas. And instead of returning data, it returns fetch response with a list of preferred replicas for each partition. This way, this request is small because this is only metadata. And then in the next fetch request, customer communicates directly with this rack A replica, so the replica that lives in the same rack where the consumer is. And we need to remember that this first two steps, so communicating with any Redpanda to get metadata and communicating with a leader to fetch this preferred replicas, that will only happen once whenever a consumer starts, because then after it learned about the closest replicas, it will only use them to actually read the data. So this way, this last message that is exchanged between rack A replica and consumer is exchanged within the AZ without crossing the AZ boundaries, and this allows us to basically not to pay for that traffic.
Amazing. Thanks for that comprehensive explanation again, Michal. So I think we now have a working mental model to understand how this follow fetching works. So there are a couple of obvious questions in terms of the sequence of operations here. So first question, what happens if the follower goes down, and how Redpanda would react in such a situation? What are our fault tolerant mechanisms?
That's a great question, and this really boils down to the question of what happens in general when a broker goes down, because there's not really a difference here. And by default in Kafka protocol, this failure handling is all based on retries. So in this case, if rack A replica will be down, like in this sequence diagram, the consumer will try to communicate with it. It will return probably like either a timeout or a connection error or something like this. And then the first step would be to communicate with any Redpanda to retrieve a new list of leaders. And then the whole sequence will happen again. So it will communicate the leader to get the closest replica. And right now there is a question: what if that is the only replica in that in that rack? Then we will return obviously the other one from the other rack, and probably this follower will be, if there is no available replica, it will be communicating with leader, because this replica is down and we cannot read from it. So it will keep communicate with leader until the replica will be alive.
Okay, understand. So the second scenario would be the follower is still available, but for some reason it becomes slow and it is lagging behind this the leader, and it can't catch up with the leader for some reason. In that case, how can we ensure the consumer is getting the consistent view of the messages as they are published to the leader? Is there any explanation?
Yes, so there are probably like a few different scenarios in this case, because there are scenarios like one of the examples is that the high watermark wasn't propagated from the leader to the followers, and in this case, this follower will, like, Redpanda, if it's isolated, doesn't have any way to communicate to the follower that I don't see any data. But followers have usually Kafka clients have this mechanism to refresh metadata every interval. So even though the follower is trying to communicate with this one broker, and let's assume that it's only communicated with that broker and that follower, because that's one partition scenario, every configurable interval, it will refresh metadata. And this way, it will send this first phase. And it will see that the node that you're trying to communicate is out of date. Because in Kafka protocol, there exists a field called leader epoch. And this leader epoch is allow a client to recognize whether it's committing with a node which is out of date. And this way, the whole process will start again, so that the whole retry loop will start again. And yeah, so this is basically how will it work. There are probably a few different scenarios, but maybe not that interesting.
All right. That answers our questions. Thanks, Michal, for the explanation again. I think now we are ready to see everything in action. So like I mentioned in the beginning, Michal has put together an amazing demo. So what I'm going to do right now is I'm going to stop sharing my screen, and I will transit back to Michal. So Michal will share his screen.
Maybe before we jump into the demo, there's a great question in the chat if you want to address that.
Sure. Yeah, so the first question is, would that cause any changes to the partition leader balance when we do auto cluster balancing? That's a great question from Christina. Michal, can you answer that question? Can you take that question?
Sure. So right now, follower fetching doesn't influence the partition balancer, but we have some plans in future to provide a way to control that in more sophisticated way.
Okay. Hope that answers your question, Christina.
So right now, basically, just to sum it up, maybe because that was maybe a little bit too cryptic, but just to sum it up, right now, the balancer will behave, the leadership balancer will behave exactly the same as it behaves right now. So it will try to even out the leaders across all the available nodes.
Okay. Hope that makes sense. And there's a follow-up question to that, Michal. If you have too many consumers consuming one particular broker, and how would that be prioritized? Will there be something like a load balancing mechanism? Can you shed some light into that?
Sure. So this is very good question. And basically, so if we have only one follower in this particular rack, then there's a little bit of like, imagine a situation in which you have lots of applications in the same rack where there is only one Redpanda node. And this way, like, and all of them are in this rack and wants to consume from that particular follower. Then we have like nothing to do because we cannot prioritize them, like we cannot move them anywhere else. But in case if there are multiple Redpanda nodes in this particular rack, then we are returning a random one for each follower. So there should be a uniform distribution of follower consuming from the replicas being in the same rack where the consumers are.
Awesome. So just a reminder to the audience. So if you have any question, please feel free to add to that Zoom chat so we can have them answered in real time. And with that question, I think we can segue into the demo. So Michal, you can take over from here.
Michal,
Can
you're
you see
still
my
mute.
screen? Sorry,
Yes.
I was muted. Sorry.
Yes,
Usual
Michal, we can
problems.
see your screen. So you're good to go.
Okay, great. Thank you. So what I have here is a 3 nodes Redpanda cluster running in Docker Compose. I can show you this here. So this is our console. And so we can see 3 nodes, right? Each of them is assigned in different AZ. And in this cluster, we have one topic, which is called follower fetching demo, FF demo, and it has 12 partitions.
Sorry, Michal, sorry for the interruption. Could you
Sure.
zoom in the screen so that?
Of course, yeah.
All right. Yeah,
So
I think that would be better. Yeah.
Once again, going over the cluster status. So this is cluster that has 3 nodes in 3 different AZs, AZ0, AZ1, AZ2. So each broker has different AZ assigned, rack assigned. And we have one topic, which is replicated on 3 nodes. And this rack awareness is enabled in that cluster. So this topic has 12 partitions. And now let me go back to my console, to my terminal, and I will start producer here. So I'm starting producer here. So this is producing with like 5 megabytes per second of data. And we can see it right here where I have this graph on a dashboard. Maybe I will zoom that out a little bit so that it's more readable.
What kind of producer is that? Is it like a Python or a script or something like that?
No, I'm I'm using librd Kafka Produce right now.
Okay, all right.
Because it has nice. It's like one of the examples from librd Kafka. It has a convenient way to throttle throughput and also a convenient way to set properties that I need for consumers. This is why I decided to use librd Kafka.
Got it. Makes sense.
And so basically, I just wanted to show you this, which is Kafka RPC. So those are the metrics that are exposed by Redpanda for Kafka RPC endpoints. And we can see here number of bytes received from the clients in valid requests, that all of the nodes, right? All of these nodes, they are receiving roughly the same amount of data, because as Christina asked about this leadership balancer, so we have this roughly balanced number of leaders per node. So they are basically all receiving data. And now there is nothing really sent to clients back, only 128 bytes per second, because those are only produce requests, and the only data returned back to clients is really a metadata about the produce records. Now let's run standard consumer here. So I will run the consumer again, librd Kafka consumer, and let's see what happens. So obviously, number of bytes sent to clients should increase, right? Because we are right now reading some data, so we are actually asking Redpanda to send us some data. Let's wait just a second to see what happens. Right. So we can see right now that there is this 5 megabytes per second roughly sent from all of the brokers, right? So this is standard and this is expected because this is standard fetching. So all the consumers are communicating with partition leaders. And now let's wait maybe for just one point of this graph to render. Yeah, so this spike in here comes from the fact that we were actually reading the data that were not yet read by the consumer. So the consumer was reading from the point where it left off. And right now that should stabilize roughly at the same rate as the produce. Right. And so now just not to wait here, I can show you this in this console that this consumer that we are reading, right? And some of the partitions are still have some lag, but that should clear out at some point. So you can see that this lag is decreasing, right? So that this consumer is actually consuming this data pretty effectively. Yeah, so yeah, exactly the same traffic goes in and the same traffic goes out. And now let's try to run this follower fetching consumer. So I will briefly show you what changed, right? So this follower fetching consumer is running this client with consumer property that says that I want to read from AZ1. Right? So this is this property that controls a fetch request content, and it's setting client rack. So this means this way a client informs the broker about its locality, its location.
Right.
Okay, now let's try to run this. And so again, we are catching up with the lag. But now what we should be looking here at, we should be seeing that all of the bytes, like most of the bytes, most of the data are returned from the broker being in AZ1. So this is this yellow line. So you can see here that indeed this increase in the traffic, as we saw before, is on all of the nodes, but right now it's limited to that one node in AZ1, right? So you can see that the consumers, they are effectively communicating with only nodes in AZ1, and again we should be seeing here some lag that is decreasing.
Yes.
And indeed, we see that we are communicating with that AZ. And if I would change that little script that tries to consume data from Redpanda and set it to AZ2, say, the same situation would happen. So that all traffic would come from AZ1, from the AZ where we want to consume from, where the consumers are.
Yeah, amazing. So the only thing that client should configure at this point is the client.rack property, isn't it? And then that will tell Redpanda that the consumer would like to read from this rack origin, isn't it, Michal?
Yes and no. So basically, there are a few things that has to be configured, because obviously, in order to use this follower fetching, we need to set up Redpanda to be rack aware. So we need to set up Redpanda to have rack ID set. So we need to tell nodes where they are located. Obviously, they may all be in the same rack, but still they should have rack configured. Then we need to have rack awareness enabled in the cluster. And then we have to configure the client rack in our clients. And this is client dependent. This property is always named the same, but the way how we set it up depends on the client.
Yeah, that makes sense, Michal. And then I think we can see everything in place.
Yes. So I will stop sharing my screen.
Yes, and thanks for this amazing demo, Michal. I think we were able to see everything in action in real life with the live demo. So before we get back, so we have another question coming from the community. So I'll read out the question. Thinking about migration here, will there be a problem if I have some clients configure that are aware of rack and some don't? So there can be a mix of clients who have configured rack awareness and some don't. I would assume the ones without will be business as usual. So would you like to take that question as well?
Yeah, exactly. That's a great summary. Business as usual. So they will, nothing will change.
Okay.
For all the clients. So this feature is working on the opt-in base. So the client has to be configured specifically to leverage that feature.
All right. Okay. Thanks, Michal, for that amazing demo. And then we reach the final segment of this meeting. So let's talk about the takeaways. So things we need to keep in mind when we configure follow fetching in production. So just to wrap things off, I would again like to invite Matt to share his thoughts, especially learn from the customer deployment all over the places. Matt, can you walk us through these things to remember?
Yeah, happy to, Denise. It's a great segue from the previous question, which is addressed here. And again, we've already had this in beta for a while, for a few weeks now. But even before that, I've been talking with customers about their use cases and, answering the tough questions, which you see some of here. We've even had some interaction with customers, very recently that pointed us to a bug that we fixed already during the beta period. So really good interactions happening with customers as they move closer to having this in production. So that's great. The things to remember are what was just mentioned, which is if you have clients that don't have rack awareness configured, or more specifically, more accurately, the rack configured in the client configuration, then they won't participate in follower fetching. So you might have rack awareness configured on the cluster side. You might have racks set on the cluster side as well. So each broker has a rack ID. But again, the client has to opt in, as Michal said, to use the feature by setting simply the client.rack property. This is how the cluster knows where the client is, knows what AZ the client's in. If you have a mix of clients who have done that configuration and some who haven't, the ones who have get the benefits of follower fetching, the ones who haven't don't. So that's just kind of a reality of the Kafka protocol that we are dealing with and maintaining strict compatibility with the Kafka protocol, is that the clients actually have to declare where they are. They're not auto detected via their IP address or anything like that. The second thing is knowing whether your consumer load is well distributed across zones can be important under heavy load when you have to balance the considerations of the cost savings of follower fetching with just the throughput and the load being put on your system, and at certain limits that starts to affect latency and things like that if everything is hotspotted in one place. So what this really means is if you have consume load that's not well distributed and you use follower fetching, then all the consumers, of course, will be going to particular AZ. If you have only a few brokers or only one broker, for example, and a single AZ, that could potentially be a problem. You save on the cost, but you put all the traffic onto one node of your 3-node cluster or one AZ in your 3 AZ cluster, for example. So it's hot spotting. And depending on whether this is availability zones, which cloud, the cloud pricing, or on-prem, right? Like one problem, one consideration could be more important than the other, right? So it works best when you have consumers that are distributed around the racks, around the AZs, around the regions, somewhat evenly, or at least there's some load coming from all three zones or all the zones. It'll be a better use of your resources. And then finally, this isn't the whole story, right? So consume workload, like I showed in the example earlier, can be many times more than the produce throughput, right? The ingress traffic, but it's not all of it. There's the ingress, there's the produce, which still incurs across AZ costs. So as of today, with Kafka and with Redpanda, it's the same. The leaders are still the ones accepting all the writes, all the produced messages and batches, and that's going to be a single leader for each partition. And so that part of your workload will still incur the whatever cross AZ costs are there for the produced workload that you have. Having said that, a future version of Redpanda is going to eliminate this problem by allowing you to pin the leaders of a given partition for a given topic, right? All partitions for a given topic in a particular region, right? Or particular AZ. So again, here, if you know the workload well, you know where the ingress is coming from in a particular AZ or particular region, you can place the leaders as opposed to being sort of load balanced around the cluster as they are today with Redpanda for efficiency. With automatic leadership balancing, you can bias the cluster to say, no, I'd like to have all the leaders for topic A, because I know the workload, I know this pipeline, I know this particular topic is getting all its data from this region or this AZ, and this other topic is coming from over here. So you can really more effectively develop these very efficient multi-AZ or multi-region clusters with leadership pinning. And that is going to allow you to, for a given topic, again, if you know where the produce and the consume is coming, completely eliminate, the cross AZ costs associated with the clients, right? There still will be cross AZ traffic for replication. Of course, we're doing that for DR purposes, right? But not for our producer consume in a future release of Redpanda that we have coming up in the near future. So that's something to keep in mind, but more good news on the way to further sort of cost optimize running Redpanda in the cloud.
Well, thanks, Matt, for that insight. So audience, please remember. So you need keep these 3 points in mind when you enable follower fetching in production. That will help you smooth performance over your cloud when you especially have this cross AC traffic flowing through multi-AC and multi-region deployments. All right, I think that wraps up our discussion today. And since we have a couple of minutes remaining, so we can take some additional questions from the audience. So now it's your time. All right, there's another question. So what are the metrics we can monitor on the followers, given just to make sure that the consumption is happening in order, in good order? Michal or Matt, you can take this question.
Yeah, I think Michal probably is the best person to answer that question. But monitoring diagnostic tools, we saw some of it in the demo, obviously.
Yes.
Okay. Yeah, thanks. I was actually going to refer to that. So Redpanda is exposing a lot of different metrics, and there are some metrics that will definitely allow us to monitor this. So one of them are the one that I showed you during the demo. So those are the bytes returned in Kafka requests. They're directly showing us the traffic that the clients are receiving from Redpanda. So this way we can monitor from where they where they consume. And we also have more detailed storage metrics where you can see how many batches, how many bytes are read from particular nodes. So if we know the application characteristics, we can basically explore these metrics to create some alerts and so on. And I think we should also remember about the metrics that the cloud providers provide, right? The cloud provider expose. So you will always see that in your monthly billing whenever you were consuming from the followers or producers. But maybe that's too late. It's better to have feedback earlier.
I hope that answered your question. So yeah, I think we can take one more question. Since we are at the top of our hour, so can probably wrap up for the day. So remember that this call is being recorded, and the recording will be available on our Redpanda YouTube channel next week. So keep watch out for that. And then with that question, I'd like to wrap up the session, and I would like to thank both Matt and Michal for your contribution today. And we learned many things regarding follower fetching, especially why we built it and how it works, and how you make it put that into a good use in your production. So that sums our discussion today. And if you have any questions further to this, you can always refer to our Redpanda community Slack posted in the chat. You can join there and ask any questions when you have any questions. And remember to try out our beta release 23.2. Yeah, so that's all. And thanks everyone, and have a good day.